All right, so yeah, we're looking at this process from A to B. Let's define that to be delta V, and that is the change in volume of the gas. And so the work along segment AB, we'll say PA for pressure at A. Could have just as well said PB, they're the same thing. But we'll say that's minus PA delta V. And now let's go from B to C. Well, that's 0. And then from C to D, now we're going from right to left, so the work is positive. And let's call that PC delta V. So, PC or PD, doesn't matter. And finally, from D to A. That's 0. It's a vertical line. So the work over the cycle we can factor out the delta V. See how we want to write this. We could say, I'm going to say PA minus PC times delta V. So we have minus PA plus PC, so that works out. Okay, now PA minus PC, or PD, same thing. For now, let's call that delta P. So the work for this cycle is minus delta P delta V. Now that's for this particular kind of rectangular process in the PV diagram. But if we look at this delta P times delta V, that'd be the area of this rectangle. And again, this result is true in general. If you have say a clockwise cycle in a PV diagram, the work is going to be the area enclosed by that cyclic process, by like the curve that it's tracing out. And if it's counterclockwise, it's going to be the same magnitude, except it will be positive. And again, this is going to be very important later when we're going to talk about engines. Like here, from A to B, we have negative work. That's negative work being done on the gas, or alternatively, that's the gas doing positive work on its environment. And again, if you have a cylinder expand, if you say push, or if you have a gas expand and you work on its environment, you can convert that expansion into some useful form of work. Like a car has multiple cylinders, typically 4 these days, and it turns that back and forth motion of the cylinder. There's something called a crankshaft, which turns that back and forth motion into circular motion, which ultimately connect to the tires and make the car move. Or steam engines, like those old-fashioned trains, work the same way. But in order to do that, you need a cyclic process. You can't just have something expand and then just stop there. I mean, you have to be able to return it to its initial condition in order to repeat the process and continue doing work. And so the idea, if we look at this very simple process, we're getting useful work here. And then if we were just to go back along this line, back to our starting point, that would not be very useful at all. Because here, the gas is expanding and doing work on its environment. To get it back to its initial state, we would have to do work on it. And the work would be the exact same if we just followed this line backwards. So one way you can get this to be a useful process is if we lower the temperature. If you just drop the pressure down, we can do that by cooling the gas. And so, the pressure would drop down. And now we'd have to do work to get it back to its initial volume. But now, because of the lower pressure, we don't have to do as much work. And so, Yeah, we'll talk more about engines later, but just this idea of a cyclic process where the magnitude of the work is equal to the area enclosed by the curve. So we talked about two processes, isobaric and isovolumetric. I want to talk about another process, very important one. Finish erasing this. And the name is very suggestive as well. We also have something called an isothermal. So an isothermal, remember iso, you know, same, thermal, well, temperature. So this is a process that occurs at a constant temperature. So let's look at our ideal gas law. So we have a fixed amount of gas, so N is fixed. R is the universal gas constant, well, that's obviously constant. And if the temperature is constant, the entire right side is constant. So if we look at our PV diagram, we have P times V is a constant. So if the volume is small, the pressure has to be high. If the volume is high, the pressure has to be low. And we're going to get a curve that looks like this. Specifically, this is a hyperbola. Like mathematically, if you have like the simplest example, xy equals 1 or y equals 1 over x, it looks like that. And so that's what an isothermal process looks like on a PV diagram. And if we want to know about the work, say we go from an initial volume to a final volume, let's look at our definition. We go from an initial volume to a final volume. I'll just write it out in a few steps. Now we can write the pressure as nRT over V. And in this case, the temperatures N and R are fixed. Of course, we have a fixed amount of gas. Temperature is constant. In this case, all this is constant. We can take that out of the integral. And so we have this integral of dV over V. And just like, the integral of 1 over x dx is a natural logarithm. Evaluated at the two limits. We don't have to worry about the absolute value sign because we're talking about volumes. And so that's always going to be positive. Now, I'm just going to look at this. I'll just work this off to the side. Here we have natural logarithm of V final minus natural logarithm of V initial. We can write it, as this ratio, V final over V initial. We could, do it like this, plus natural log of V initial to the -1. And remember, when you have this basic property, say natural log of xy would be natural log of x plus natural log of y. So your natural log of Vf plus natural log of Vi to the -1 is a natural log of Vf times Vi to the -1. So we can write our final result. I'll do that here. And this is for an isothermal process. So, again, another kind of special process. We have isobaric, isovolumetric, and isothermal. All right. There's one more type of process that's important that we give a name to. But before that, I want to kind of revisit this idea, first law of thermodynamics. We talked about the 0th law, which is what makes defining temperature possible. It's based on this idea of thermal equilibrium. And, logically, two things could be in equilibrium. Maybe many conditions would have to be true in order for them to be in equilibrium. Maybe pressure could be a factor, or density, or mass, or whatever. But what the 0th law says is that if A is in contact with B, or if A is in equilibrium with B, B is in equilibrium with C, then A is in equilibrium with C. And so next comes the first law of thermodynamics, which is really just conservation of energy. However, this topic of thermodynamics, this subject, was worked out in the 1800s, and they didn't fully understand the connection between heat and energy at the time. So for historical reasons, it's called the first law of thermodynamics. But E internal, or EINT, that's the internal energy. And we write that as Q plus W, where Q is heat, W is work. And again, the convention is, say we have a gas with a movable piston. So W is the work done on the gas. And so if you say push the piston down, you're doing work on the gas. Well, what's going to happen if you compress a gas? It's going to get hotter. It's going to gain more energy. Well, it's going to gain energy, and as a result, it's going to become hotter. So if you do work on the gas, you are giving it energy. And so, it's good to look at these kind of one at a time. Say Q is 0. So if you do work on a gas, internal energy should increase. That's why I don't like memorize these conventions. If you know this equation, put that on the equation board. I guess we can write the ideal gas law as well. But anyways, that's the first law of thermodynamics. And that shows how the internal energy, so W, that's work done on the gas. So if, say, the piston is moving up, the gas is expanding, that means it's doing work on the environment, and W would be negative in that case. So the gas is doing work, energy is transferring from the gas to its environment, and so the internal energy of the gas would be decreasing. And Q is heat exchange, and heat can go either direction as well. And so let's say heat is entering the gas. That would make Q positive. If heat is entering the gas, that would cause its internal energy to increase. So here, this would be Q greater than 0. Let's say heat is leaving the gas. That would make Q less than 0. So if heat is flowing from the gas to its environment, the gas is cooling off and losing energy. So if Q is negative, heat is flowing out, internal energy is increasing. Now both of these can occur at the same time, so just as far as a convention is concerned, it's best to just look at them one at a time. Okay, so that's the first law of thermodynamics. Now, I mentioned there's one more process we want to consider, and that's called an adiabatic process. And what that means is basically just Q is 0. That means a process occurs without heat flowing into the gas or out of the gas. One way that could happen is if you have something that occurs very rapidly. Maybe there's just no time for heat to escape. Or maybe if it's extremely well insulated. But an adiabatic process is very important as well. And we can see right now, for an adiabatic process, this one's a little different than before, work would just be equal to the change in internal energy. Now later on, we're going to show this result for an adiabatic process. That we know for an isothermal process, we know that the pressure times the volume is a constant. For an adiabatic process, you have PV to the gamma is equal to constant, where gamma is a number, typically greater than 1. And we can then calculate the work for an adiabatic process using the ideal gas law and this result, but we're not there yet. So I'll just mention this one looks a little different right now. It's related to the internal energy. But we can get another expression for the work for an adiabatic process later. All right. I think that'll be it for this video. Just basically work. It's all about work done, and this is a very important topic. And these PV diagrams also, they really contain all the information about the gas. For any given gas, if you know the amount, either number of moles or the number of particles, because every point on the graph gives you the pressure and the volume, and if you know that, you can find the temperature. So that'll be it for this video.